Bismillahir Rahmanir Rahim. This video is about lower semi-continuous functions. These functions are very relevant to convex analysis and optimization. However, in this video, I just focus on the property of lower semi-continuity. So function f here does not need to be convex. We have a function f, the domain is Rn, and function f is an extended real valued function. So we allow f to take the value plus infinity. Function f is lower semi-continuous, LSC, at a point x0, if for every lambda that is less than f of x0, so if this is x0 and the value of the function here is f of x0, then for every lambda that is strictly less than f of x0, there exists an alpha, and this alpha, of course, will depend on lambda, such that fx is greater than lambda for every x in the ball with center x0 and radius alpha of lambda. So this means that if f of x0 is greater than lambda at a point, then f of x is greater than lambda in a neighborhood of that point. This is simply what this definition means. Again, if f of x0 is strictly greater than lambda at the point x0, then there is a neighborhood, there is a ball with center x0 and radius alpha that will depend on lambda, such that for every x that is in this ball, we have the inequality satisfied at x0 satisfied at every x in the ball. So f of x is greater than lambda for every x in this ball. The notation that I'm using here, b of a bar comma r. So this is in the n-dimensional space. This is a ball. The center is a bar, which is the first argument here, and the radius is r. This is the set of points x in the n-dimensional space that are at a distance from a bar that is strictly less than r. So this is what we will take as the main definition of a lower semi-continuous function. But now we want to find like equivalent definitions that will be useful when we study convex analysis, optimization theory, and so forth. Before giving an alternative definition, an example of a lower semi-continuous function. So we have f from R to R, and let's say that this is the point x0, and let's say that f looks like this. And here is the value f of x0, and this is our function. Now, according to the definition, now for any value lambda that we choose that is less than f of x0, there should be a neighborhood of x0. And in this neighborhood, f of x is greater than lambda. So let's take a lambda, this value here. So this is lambda. And do we have f of x greater than lambda in a neighborhood of x0? Yes. If we take this neighborhood, you'll find that the value of the function here it is. And it is indeed greater than lambda in some neighborhood of x0. So this function is lower semi-continuous. To make things clearer, let's actually do a slight modification to this function. So I will take the same function, but rather than making this value f of x0, I will take this upper value to be f of x0. So this is our function now, just this change at x0. Now, is this function lower semi-continuous? If we choose lambda here, so this is a valid value of lambda, it is less than f of x0. But is there a neighborhood of x0 at which f of x is greater than lambda? Now, if we take any neighborhood of x0, so this is x0 here in the middle, now you'll find that this part of the function is actually less than lambda. And no matter what you do to your interval about x0, no matter how small it is, we will not be able to find an interval about x0 at which f of x is greater than lambda. So this function is not lower semi-continuous. This one is, but this one is not, just by doing this change here. If we just say that function f is lower semi-continuous, then we mean that it is lower semi-continuous at all points in Rn. So the definition here is at a point x0. If we just say the function is lower semi-continuous, then it is continuous for every x in Rn. Let's now move to an alternative definition for a lower semi-continuous function. F is LSC at x0, and here we will require that f of x0 is less than infinity. Note that our function is extended real valued. Sometimes it is useful to make f of x equal to plus infinity for some x values. So here we have x0, and f of x0 is less than infinity. We say that the function is lower semi-continuous if for every epsilon that is greater than 0, there exists a delta, which generally will depend on this epsilon, such that for every x that is in the ball with center x0 and radius delta, so in this neighborhood of x0, we have that f of x0 is less than f of x plus epsilon. The nice thing about this definition is that it clearly gives the difference between a continuous function and a lower semi-continuous function. For a continuous function, so if f is continuous at x0, then for every epsilon greater than 0, there exists delta, which generally depends on epsilon, such that for every x that is in the neighborhood, in the ball, with center x0 and radius delta, what do we have? We have that the magnitude of f of x minus f of x0, that this is less than epsilon. This means that f of x0 minus f of x is less than epsilon, but greater than minus epsilon. So this means that f of x0 is less than f of x plus epsilon if we take this inequality. And if we take the other inequality, we find that f of x0 is greater than f of x minus epsilon. Now, if we go back to the definition of a lower semi-continuous function, we find that we have one of those inequalities and not the other. So if the function is continuous, then these two inequalities must be satisfied in some neighborhood of x0. We must have that f of x0 is strictly less than f of x plus some positive epsilon, and f of x0 is strictly greater than f of x minus epsilon. For a lower semi-continuous function, we are more than satisfied with just one of these inequalities, and this may explain the word semi-continuous. It's like half continuous. One of the two inequalities is relevant, and you can guess that there is something called an upper semi-continuous function. For an upper semi-continuous function, the focus will be the other inequality. For lower semi-continuous functions, we want for an x0 such that f of x0 is less than infinity. We want for every epsilon that is strictly positive, there is a delta such that the ball with center x0 and radius delta, over this ball, for every x in that ball, we have f of x0 strictly less than f of x plus epsilon. Now we want to prove that these two definitions are equivalent when we have f of x0 less than infinity. Let's do the first direction. Suppose that the main definition is true. The main definition, as a reminder, the main definition is that if f of x0 is greater than lambda, then there is a neighborhood of x0 such that in that neighborhood, f of x is also greater than lambda. Suppose that this is true, and now we will try to show that the second definition is true. So if the first definition is true, consider a strictly positive epsilon. Now we have, this is the value of f of x0, and definitely it is strictly greater than f of x0 minus epsilon for this given positive epsilon. Choose lambda that is between f of x0 and f of x0 minus epsilon. Because f of x0 is strictly greater than f of x0 minus this positive epsilon, then we can always have a lambda that is somewhere between these two guys. Note that the first definition is now assumed to be valid. If we choose a lambda such that lambda is less than f of x0, then there is a neighborhood. There is a ball with center x0 and radius alpha, which will depend on lambda, such that for every x in this ball, we have f of x is strictly greater than lambda. Note that lambda is greater than f of x0 minus epsilon for any given epsilon. Then for every x in this ball, we have f of x, which is greater than lambda, is also greater than f of x0 minus epsilon. Then for every x in that ball, we have f of x0 strictly less than f of x plus epsilon, which is the second definition. So again, the idea, we start with f of x0. Challenge me with any epsilon that is strictly positive. If there is a positive epsilon, then definitely f of x0 minus epsilon is strictly less than f of x0. And between these two quantities, I can choose any lambda. Now this lambda is less than f of x0. Then by the original definition of a lower semi-continuous function, there is a neighborhood of x0. And in this neighborhood, f of x is greater than lambda. So in that neighborhood, f of x is greater than f of x0 minus epsilon. And we can do this for any positive epsilon. Just move epsilon to the other side and we get the second definition. So there is a neighborhood of x0. And in this neighborhood, for every x in this ball, we have f of x0 strictly less than f of x plus epsilon. And we can do this for every positive epsilon. So if the first definition is true, then the second one is true. Now let's do the other direction. So suppose that this is true. Second definition is true. Now choose any lambda that is less than f of x0. This is f of x0 as a value, and strictly less than f of x0, we have lambda. We can always find that epsilon, a positive epsilon, such that if we subtract epsilon from f of x0, we are still greater than lambda. So there is a positive epsilon such that f of x0 minus epsilon is superior to lambda. The second definition is true. From the second definition, given any positive epsilon, we can find a positive delta such that for every x in the ball with center x0 and radius delta, we have f of x0 less than f of x plus epsilon. So for every x in this ball, we have lambda less than f of x0 minus epsilon. Now f of x0 is upper bounded by f of x plus epsilon. So lambda is less than f of x. We started with a lambda that is strictly less than f of x0. We have found that there is a neighborhood of x0 such that for every x in that neighborhood, we have lambda strictly less than f of x. And this is the first definition. So these two definitions imply one another. Let's now study another characterization of a lower semi-continuous function. And this characterization is concerned with the sub-level sets of the function. So we are here interested in the set of x values in the n-dimensional space such that f of x is less than or equal to small gamma for some specified gamma. So this set here denoted by big gamma and the subscript which is a small gamma, again, it's the pre-image of this interval here from minus infinity to gamma. It's the set of points in the n-dimensional space that satisfy this inequality, f of x less than or equal to gamma. The value of the function is gamma or less. Here is our claim. The function f is lower semi-continuous, and I don't say here at x0, so we are talking about the function being lower semi-continuous at every point in the n-dimensional space. F is lower semi-continuous if and only if the sublevel set is a closed set for any choice of small gamma. Let's prove this statement. Let's assume first that f is lower semi-continuous and show that the sublevel set is indeed a closed set. We know from analysis that to prove that a set is closed, one way of doing the proof is to show that the complement of the set is an open set. And this is exactly what we will do here. We will choose some x tilde that is in the complement of the sublevel set with parameter small gamma. Since x tilde is in this set, then x tilde satisfies the inequality that f of x tilde is strictly greater than gamma. Because for any x that is in the sublevel set, the function is less than or equal to gamma. So if x tilde is in the complement, then f of x tilde is strictly greater than gamma. We have gamma, and gamma is strictly greater than f of x tilde. Now, what is a lower semi-continuous function? If the value of the function at some point exceeds gamma, then there is a neighborhood of that point, and in this neighborhood, the value of the function is also superior to gamma. In other words, f of x tilde is greater than small gamma, and f is a lower semi-continuous function. So there exists alpha, which generally depends on gamma, such that for every x in the ball with center x tilde and radius alpha, what do we have? We have that f of x is also strictly greater than gamma. This means that we have a point x tilde, and at x tilde, we have f of x tilde greater than gamma. Now, there is a ball about this point with some radius alpha, and what is going on in this ball? What is going on is that for every x here, f of x is also greater than gamma, which means that the ball is in the complement of the sublevel set with parameter small gamma, because we have that f of x is greater than gamma. This means that the complement is an open set, because if you choose any point in the complement, then there is a ball about that point that is also contained in the complement. This is the definition of an open set. The complement of this big gamma of the sublevel set is an open set. So the sublevel set itself is closed. And this is true for any gamma in R. Now let's investigate the other direction. So in the other direction, we will assume that for every small gamma that is a real number, that the sublevel set is a closed set. If the sublevel set is a closed set, then the complement is an open set. Now choose x bar in the complement, which means that x bar will satisfy the inequality that f of x bar is strictly greater than gamma. Now, because this set is an open set, then there is a beta that is strictly positive, such that the ball with center x bar and radius beta, this ball is totally contained in the complement of the sublevel set. Then for every x that is in this ball, we have the inequality that f of x is strictly greater than gamma. Let's see what we have. We have f of x bar strictly greater than gamma. We discovered that we can find the neighborhood of this point, and in this neighborhood, every x satisfies the inequality that f of x is strictly greater than gamma. And this is the definition of a lower semi-continuous function. We have now both directions. We have proved the result that if the sublevel set parameterized by small gamma is closed for any gamma in R, then the function is lower semi-continuous. The converse is also true. Let's investigate now one of the very important characterizations of a lower semi-continuous function that is very relevant in convex analysis and optimization. So this is the characterization of a lower semi-continuous function in terms of the epigraph of the function. The epigraph of the function is the set of all points in the Cartesian product of Rn and R that are on or above the graph of the function. So in the simple case, if f is a function from R to R, then here we have x and this is the graph of the function. The epigraph is the set of points in the two-dimensional space that are on or above the graph of the function. Here we have the epigraph set of points in Rn plus 1. So we have a vector here with n plus 1 components. The first n components are z. Now, if we apply the function f to the first n components, we get a value, and this value is less than or equal to the last component, which is the scalar t, which means that t is equal to f of z, or t is greater than or higher than f of z. We want to show that the function is lower semi-continuous if and only if the epigraph of the function is a closed set. Suppose that f is a lower semi-continuous function. From the complement of the epigraph, pick a point, x tilde and gamma. So x tilde has n components, and gamma is a scalar. Because this vector in Rn plus 1 is in the complement of the epigraph, then it must be the case that f of x tilde is strictly greater than gamma. So we have here, this is f of x tilde, and here is gamma. And because f of x tilde is strictly greater than gamma, then there is zeta, such that the interval from gamma minus zeta to gamma plus zeta, all points in that interval are strictly less than f of x tilde. So we can always find the zeta, which will depend on gamma and f of x tilde, such that f of x tilde is greater than gamma tilde, and gamma tilde is any point in the open interval from gamma minus zeta to gamma plus zeta. Now we have assumed that f is a lower semi-continuous function. So this means that for every lambda, if f of x tilde is greater than lambda, then we can find a neighborhood. We can find the ball with center x tilde and radius alpha, which will generally depend on lambda, such that for every x in this ball here, f of x is strictly greater than lambda. Suppose that we choose alpha that corresponds to gamma plus zeta. Then in the ball with center x tilde and radius alpha chosen based on gamma plus zeta, then for every x in this ball, what do we have? We have that f of x is strictly greater than gamma plus zeta. But gamma plus zeta is greater than gamma tilde, which is any point in this open interval. So we have for every x in this ball, f of x is strictly greater than gamma tilde. What do we have now? In the Cartesian product of this interval about gamma, it's from gamma minus zeta to gamma plus zeta, and the ball about x tilde with this radius alpha chosen such that over this ball f of x is strictly greater than gamma plus zeta. In this neighborhood, every point satisfies that f of x is strictly greater than gamma tilde. We started with the specific point x tilde and gamma, and at this point f of x tilde is greater than gamma. Now we discover that about this point there is a neighborhood, and in this neighborhood we have every x and every gamma tilde satisfy that f of x is greater than gamma tilde. So this means that the complement of the epigraph is an open set. The epigraph itself is a closed set. Now suppose that the epigraph of f is closed. Consider any sequence xk that is in the sublevel set with parameter gamma. So this is again the set in n-dimensional space such that f of x is less than or equal to gamma. For every k, we have f of xk is less than or equal to gamma. If we take a vector in Rn plus 1, the first n components are xk and the last component is gamma, then this vector is indeed in the epigraph of f. In the epigraph of f, those vectors here, those n plus 1 dimensional vectors, as gamma tends to infinity, they will tend to x bar, because we are studying a convergent sequence that is assumed to converge to x bar, and the last component here is fixed at gamma. In the limit as k tends to infinity, the last component will also be gamma. It is assumed that the epigraph of function f is a closed set. So if there is a convergent sequence in that set, then the limit point is also in the set. Because the epigraph of f is assumed to be a closed set, then the limit, which is this vector, the first n components are x bar and the last component is gamma, is also in the epigraph. Because this point is in the epigraph, then if we apply f to the first n components x bar, then this is less than or equal to the last component, which is gamma. So f of x bar is less than or equal to gamma. This means that x bar is also in this sublevel set. We started with a sublevel set. We took a sequence of vectors in this set, a convergent sequence of vectors that converges to x bar. We don't know whether x bar is in this set or not. What we did is that we exploited the fact that f of xk is less than or equal to gamma for every k that is a positive integer. This means that the n plus 1 dimensional vectors in which we have xk as the first n components and gamma, those vectors are in the epigraph of f. If we take the limit of those vectors, then the limit is this vector with the first n components being equal to x bar and the last one being equal to gamma. What did we gain from this step? We have a starting point, which is that the epigraph is a closed set. Since we have convergence to a limit and our set is closed, then the limit is in the set itself. So the vector in which the first n components are x bar and the last component is gamma is in the epigraph of function f. F of x bar is less than or equal to gamma. But this means that x bar is in this set here, the sublevel set with parameter small gamma. We started with a convergent sequence in the sublevel set, and we discovered that the limit must be in the set itself. Then the sublevel set is closed. And on the previous page, we have shown that if the sublevel set is closed, then the function is lower semi-continuous. And this is what we needed to show. Here is another way of looking at function f being lower semi-continuous at a point x0. F is lower semi-continuous at x0 if and only if the limit infimum of f of x as x tends to x0 is greater than or equal to f of x0. Let's prove this statement. Let's start by showing that f is lower semi-continuous if the limit infimum, which is L, is greater than or equal to f of x0. What does it mean that L is the limit infimum of f of x as x tends to x0? It means that for any positive epsilon, there is a corresponding positive delta, such that if we compute the infimum of the function f of x over the ball with radius delta and center x0, but we will exclude the center. If we compute the infimum of the function over this ball and then take the difference between the infimum and L, then this difference in magnitude is less than epsilon. No matter what epsilon is, there is always a delta such that we can make this magnitude less than epsilon. Now, if we have that this magnitude is less than epsilon, so it means that the difference here is greater than minus epsilon. So this means that the infimum is greater than L minus epsilon. It is given that L is greater than or equal to f of x0. So the infimum is strictly greater than f of x0 minus epsilon. We can move minus epsilon to the other side, and so f of x0 is less than the infimum of f of x plus epsilon. And now we can actually take the infimum over all the ball without excluding x0. Because if we allow x on the right-hand side to be equal to x0, then f of x0 plus a positive epsilon is definitely strictly greater than f of x0. So we have f of x0 is less than the infimum of f of x now taking over the ball with radius delta plus epsilon. And the infimum, by definition, is less than or equal to f of x for every x that is in this ball with center x0 and radius delta. What is the conclusion? For every epsilon greater than 0, we can find a corresponding strictly positive delta, such that for every x that is in the ball with center x0 and some radius which is delta, we have that f of x0 is less than f of x plus epsilon. And this is one of the definitions of a lower semi-continuous function. So if we start by assuming that the limit infimum is greater than or equal to f of x0, then indeed the function is lower semi-continuous. Now, let's assume that the function is lower semi-continuous. So the goal is to show that L, which is the limit infimum of f of x as x tends to x0, that this limit infimum is greater than or equal to f of x0. F is lower semi-continuous at every point in Rn, so it is lower semi-continuous at x0. And now our objective is to show this inequality. Again, what is the meaning of the limit as in the previous part? What does it mean that L is the limit infimum? For every epsilon greater than 0, there is a delta. Let's call it here delta 1. So there exists delta 1, which generally depends on epsilon and which is strictly positive, such that the magnitude of the difference between L, the limit, and the infimum of f of x over the ball with center x0, radius delta 1, excluding x0, the magnitude of this difference is less than epsilon. And if this is the case, then the difference is less than epsilon, or we can say that the infimum is strictly less than L plus epsilon. It is given that f is lower semi-continuous at the point x0. So for every epsilon greater than 0, there exists delta 2 of epsilon, which is greater than 0, such that f of x0 is less than f of x plus epsilon. This is one of the definitions of lower semi-continuous function, assuming that f of x0 is strictly less than infinity. And this is true for every x that is in the ball with center x0 and radius delta 2. We can choose delta 2 so that this inequality here is satisfied with a positive number here that is epsilon over 2. So for every x in the ball with center x0 and radius delta 2, now function of epsilon over 2. So we choose the delta 2 corresponding to epsilon over 2, such that we have f of x0 is less than f of x plus epsilon over 2. Now take the infimum of both sides of this inequality. The left-hand side is not a function of x, so the infimum of f of x0 will be f of x0 itself. For the right-hand side, we have the infimum of a function plus a constant. So this is the infimum of the function plus the constant. And so f of x0 is less than or equal to. Now we need to allow for the possibility of equality, because if we have an equality, 1 is strictly less than 1 plus 1 over n. If we take the infimum of both sides, the infimum of the left-hand side is 1. The infimum of the right-hand side is 1. The two sides are equal. So when we take the infimum of both sides of an inequality that is strict, we need to include the possibility of equality. So f of x0 is less than or equal to the infimum of f of x over this pole with center x0 and radius delta 2 of epsilon over 2. Now what if we take the infimum and we exclude the point x0? This infimum is less than or equal to this infimum. If we have S1 subset of S2 subset of S3, then the infimum of f of x with x in S1, this is greater than or equal to the infimum of f of x with x in S2, which is greater than or equal to the infimum of f of x and x is in S3. The smallest we can get if we use the biggest set. Okay, so here what we are doing is that we are shrinking, so we have less than or equal to. Let's do further shrinking to the pole. So now we will take x to be in the pole with center x0, but now the radius is not just delta 2 of epsilon over 2. This radius here will allow us to write down that f of x0 is less than this infimum plus epsilon over 2. Now we will take the radius to be the minimum of delta 1 of epsilon over 2 and delta 2 of epsilon over 2. So this pole here is contained in this pole. Why do we have this delta 1? Let's remind ourselves. Using the definition of limit infimum, we obtain that this infimum here is less than L plus epsilon. If we use delta 1 that corresponds to epsilon over 2, then the infimum will be less than L plus epsilon over 2. So this is what we want here. We will make our pole with this radius, which is the minimum of delta 1 epsilon over 2, delta 2 over epsilon over 2, so that this pole is contained in this pole. Furthermore, the radius now is delta 1 of epsilon over 2 or less. This means that the infimum can be upper bounded by L plus epsilon over 2. So this is the upper bound on f of x0. L plus epsilon over 2 plus epsilon over 2. F of x0 is less than or equal to L plus epsilon. To summarize, we have assumed that f is lower semi-continuous at x0. This means that for every epsilon greater than 0, there exists delta 2, which depends on epsilon, such that f of x0 is strictly less than f of x plus epsilon for every x that is in the pole with center x0 and radius delta 2 of epsilon. Epsilon is a positive parameter. What we do is that we will choose delta 2 that corresponds to epsilon over 2 to make the upper bound f of x plus epsilon over 2. Okay, so we have this. Now take infimum of both sides over x in this pole. Then, not a problem if we exclude x0. We will have here an inequality less than or equal to. Recall this fact here. If S3 contains S2 and S2 contains S1, then the infimum of f of x, if x is in S3, this will be less than or equal to the infimum of f of x if x is just in S2. And this in turn is less than or equal to the infimum of f of x if we use x in S1. And then we did further shrinking of the pole by making the radius the minimum of delta 1 of epsilon over 2, delta 2 epsilon over 2. Now delta 1 is the radius that will make the infimum less than L plus a positive number. So we choose delta 1 of epsilon over 2 so that we make the infimum less than L plus epsilon over 2. For every epsilon that is strictly positive, f of x0 is less than or equal to L. This means that f of x0 is less than or equal to L. If f of x0 is greater than L, then f of x0 minus f of x0 minus L over 2. This quantity here, which is equal to f of x0 plus L over 2. F of x0 is strictly greater than L. So this is strictly greater than L plus L over 2, which is equal to L. Now move this quantity to the other side. Then we have f of x0 is strictly greater than L plus f of x0 minus L over 2. And this is assumed to be a positive quantity. So what do we have? If f of x0 is indeed strictly greater than L, then there is a positive epsilon, which is given by this f of x0 minus L over 2, such that f of x0 is strictly greater than L plus this positive quantity. But this contradicts the fact that f of x0 is less than or equal to L plus epsilon for every strictly positive epsilon. So this is wrong, and it must be the case that f of x0 is less than or equal to L. And what is L? It is just the limit infimum. So for a function f of x that is lower semi-continuous at x0, we have that f of x0 is less than or equal to the limit infimum of f of x as x tends to x0.